This is OJB. Let's read, shall we? All-spin logic. The possible role of spin, rather than charge, as a state variable in devices for processing and storing information has been widely discussed, because it could allow low-power operation and might also have applications in quantum computing. However, spin-based experiments and proposals for logic applications typically use spin only as an internal variable, the terminal quantities for each individual logic gate still being charge-based. This requires repeated spin-to-charge conversion using extra hardware that offsets any possible advantage. We propose a spintronic device that uses spin at every stage of its operation. Information manipulation, transport, storage, input and output are all accomplished with magnets and spin-coherent channels. Figure 1 illustrates the underlying idea of our device. And we can see that here, Figure 1. The input logic bit controls the state of the corresponding output logic bit, with the energy being provided by an independent source, V supply. In the ASL device, or all-spin logic device, information is stored in the bistable states of magnets, which can be non-volatile. Okay, back to the paper. The building block for a future spin-based circuitry consists of nanomagnets that are attached to a channel that carries the spin current. Information is stored in terms of magnetization of the nanomagnet, which can be non-volatile. The spin current carries the information from one magnet to the other and imprints its spin information onto the receiving magnet by means of an effect known as spin torque. The magnetization information of the input magnet is transferred into the channel by driving a conventional charge current from the contact labeled V supply to the contact labeled G and D, or ground, in Figure 1. Note that this current does not flow between the two magnets, but is only used to create the desired spinning current. As long as the spin current preserves its magnetization in the channel, information can be transferred from one magnet to the other. To ensure directional information propagation, a tunneling barrier, shown in Figure 1, is introduced partly underneath each nanomagnet, and this arrangement breaks the symmetry between input and output magnet and ensures that the output magnet does not impact the magnetization of the input magnet. Another method for achieving directional information has been discussed elsewhere. That method has the added advantage of requiring lower spin signals in the channel, but in the expense of a more complicated clocking scheme. Combining elements from Figure 1 allows for the formation of any conventional circuit, since the all-spin device should satisfy the 5 essential characteristics for logic applications, namely nonlinearity, gain, concatenability, feedback preventions, and a complete set of Boolean operations. Different from the other spin-based device and circuit architectures, we are proposing here for the first time a path that does not require converting spin currents into charge currents. Instead, information is processed entirely in the spin realm. In addition, we are proposing to utilize a local spin information rather than fringing magnetic fields from one magnet to the other. For example, MQCA approach. While any fringing magnetic field that is frequently used to transfer the local and thus prohibit channeling of the information flow, our all-spin logic device, or ASL approach, ensures local switching through the use of spin currents between input and output magnets. While sufficient local field strengths can be accomplished in this way to manipulate the magnetization of the information receiving magnet, our approach does not suffer from an unintentional switching of other magnets within the various circuits. The ASL device involves two very different physics, namely 1. The transport of spins in the channel, normally described by the Vallée-Fert equation, and 2. The dynamics of the magnet, normally described by the LG equation. With the spin current incorporated, we will show that it is possible to translate both these aspects into a lumped resistor network, a circuit model where the resistors are actually 2x2 matrices having a charge component and a spin component. The resulting circuit model gives results identical to that obtained directly from the original differential equations, but has the advantage of providing a composite physical picture involving both the transport channel and the magnet. It should be noted that although the majority logic can be used to construct universal logic gates, such as NAND and NOR, alternatively, the ASL device concept, along with the analog nature of spin signal in the channel, can be utilized to enhance functionality per device. This can result in lower number of devices, lower power consumption, and lower footprint area for a given functional block, e.g. a full adder. The overall circuitry can be composed of various ASL blocks which can connect to each other via electrical interconnects for a long range and or fast interconnects. The electrical write to a given ASL block can be achieved using standard spin torque switching, while the electrical read can be achieved by standard magnetoresistance measurement. And that concludes the end of the article. That concludes the article altogether, actually. So, thank you for sticking around, ladies and gentlemen. And you can have a quick look at, not quick look, but a longer look at this spin logic device. Thank you very much. Cheerio.